Hello everyone. In this video, let's try to understand convolution integral in particular using an animation. Now, the convolution of the signal xt and ht is given by yt equals integral from minus infinity to infinity h tau ht minus tau d tau. So the variable of integration is tau. So in this case, as we know, we have a system and we characterize that system by the impulse response, and when we give an input to that system xt, we get the output yt. And how can we compute that output? That is using this convolution integral. So one more thing that we have to remember is that when we represent this convolution in this fashion, using the asterisk to represent the convolution, as it is commutative, we can interchange the signal and the system. So therefore, it does not mean very much to think that system is a system or the signal is a system. They are interchangeable. So this is called the convolution integral or superposition integral. This corresponds to the representation of a continuous time ATI system in terms of its response to a unit impulse. So in discrete time, we have a similar relationship. Xn is the signal, Hn is the impulse response. So therefore, the summation is from minus infinity to infinity, xk, Hn minus k. So we sum over k. So one more thing that we have to remember is to get one particular t, y at one particular t value, you have to do an infinite integral. So the domain of integration is infinity. So it does not mean that the integral is infinity, but you have from minus infinity to infinity, you have to integrate. And also we remember that the characteristics of an LTI system are completely determined by its impulse response. Okay, so what we want to do in this animation is to first of all take signal xt and convolve that with one impulse located at 0. So secondly, we will locate the impulse at t equals 2 and then convolve and see how the output is. And then as a third one, we will combine this and that and locate an impulse at t equals 0 and t equals 2 and convolve with xt. Then finally, we will convolve xt with a signal of this nature, right? Height is 1 and that's our ht actually, although we call it signal, it is the system. So this is 1 because ut minus ut minus 1 is this one. Okay, let's start. So what you see here is the impulse located at 0. So you can see this is the input signal. So we have to reflect it. And after reflecting, we move it to get the output at different values of t. So you can see for different values of t, the value of the signal that overlaps with non-zero values of the system, h tau, is what you get. So maybe we can see this again. So you can see this is with small t, the reflected signal x tau is moving. So okay, now there will be overlap very shortly with the impulse. Now there's an overlap. So this value right here is what you're going to see here. Okay. Alright, so here once again this is our ht and this is xt and this is h tau. So you have to just copy the same signal, and then in this one we had the ht signal reflected and located that small t in the tau axis. Then this is the output that we want to compute. So we drew that output as t changes. Yeah. So essentially, because of the impulse, what happened? Our input signal x got actually located at the impulse. So you may have seen that here. Now here, in this case, the impulse is located at 0. That's where the impulse is located. So if you take signal xt, its 0 is right here. So what will happen is this signal 0 will be located exactly where the impulse is in the output. That's what will happen. So due to some reason, if the impulse were over here, then you will have the signal located in this fashion, right? Yes. So that's the nature of an impulse, convolution with an impulse. The input signal xt gets located where the impulse is. So that you can see in the next slide. So here you can see impulse eta is at 2, t equals 2. So this is delta t minus 2. You can see the input signal xt has been reflected and located at small t along the tau axis. Now as soon as this signal starts overlapping with this, you will see a value here. Can you see that? Also what you would notice is now, for example, when the signal is like this, that means t is here. Now only non-zero value of ht is over here, and this number here will have to be multiplied, and there is a value there. Actually multiplying and summing does not mean much here because there is only one value in ht at 2 and impulse, and that number will be located at t, where t is right here, right, at this location. So therefore once again you can see the value of reflecting xt over here. So because this is the area that happens first, right, and that has to encounter the impulse first. So that's why we have taken that and reflected, and then we start moving that. Okay. So now in the next example, we will see both the impulses. So you can see both the impulses now at t equals 0 and t equals 2. So in tau axis also they will be the same. So you take xt and reflect that and locate at t in the tau axis. Now you will start seeing a value. Okay. Now once again it hits the other impulse, then the combination of those will come into the picture. Yes. Okay. So that's an important thing that you saw here. There are two impulses. So due to the first impulse, now this first impulse is actually ht equals delta t. ht equals delta t. And so you can see due to this reason, this system does not have memory. The output value at t depends only on the input value at t. Output value at a particular t only depends on the input value at that particular t. That's what happens when you have only delta t. So there is no memory. So therefore, whatever that you give as the input will be just multiplied by a constant. Now here, of course, this value is 1. That means when you multiply and integrate, the area will be 1, and then as a result this xt gets located there. So that's what happened in particular in the very first example that we saw. Right here you saw that this signal got located there, and here in this case it's t minus 2. The system has memory, So what that means is due to the inputs happening over there, output resulted at a later time, right? Can you see that? Yeah. Okay. So here in this case, this impulse is there, this impulse is there. So the output at some time points will be a combination due to both these, because when xt minus tau overlaps with this and that, those will have to be summed up. It doesn't happen yet. Right now it is happening. Can you see that? Right now it is happening. So that's why this combination is there. Okay. So I hope that point is clear for you. So it is very easy for us to understand something like an amplifier, which is a memoryless system. Without reverberation and so on, it's a memoryless system. Let's say it just multiplies by 2. So if it is just multiplies by 2, ht is like 2 delta t. So it just multiplies. But when there is a response like that, some kind of a reverberation, then the output is slightly complicated. But now here we only consider two impulses, one located at 0 and the other one located at 2. Actually, the impulse response is also a continuous time system, so we can consider ut minus 1, something like that. So now you see the once again we are moving reflected xt along the tau axis located at t. Now you can see the value will start. Okay, so we have to find the overlap and multiply. Yeah. You can see how that happens, right? So long as there is an overlap between x tau and x h tau and xt minus tau, uh, x tau and ht minus tau, you have to multiply these individual values and sum them up. Of course, in continuous time, you have to multiply and integrate, right? Multiply and integrate. So that's what happens here. So let's look at it once again. So no overlap yet. No overlap. No overlap. When t reaches 0, there will be overlap. Overlap will start. Overlap is starting. Now you can see an output happening. Yeah, still there is overlap, right? Can you see that? Okay. So what we wanted to see in this animation was to see how the output of a system, a linear time invariant system, is computed through convolution. So now you saw why xt has to be reflected, because what happens first must happen first along the time axis. So if there is a single impulse at t equals 0, the output will be the xt just located at that point, that is x yt will be xt located here. So but when you have something like delta t minus 2, xt gets located at t equals 2, and then when you have a combination, these two things will be added. So xt at t equals 0 and delayed xt will be added together when you have delta t and delta t minus 2. But the actual general situation is your impulse response will be a continuous signal like that, not just a combination of impulses. They are also continuous time signals, and then you have to find multiply the overlapping area and sum, or actually because these are continuous time signals and systems, you have to integrate. So some questions that would arise is in convolution operation that happens on images. For example, Sobel filtering or Gaussian filtering or average filtering. Do we have to do this reflection? Um, Actually, if your filter is not symmetric like a Gaussian filter or a Sobel filter, you must do the reflection and then carry out the convolution. Otherwise, the output that you get will be a reflected version of the so-called convolution kernel working on the image. But the thing is, Gaussian kernel and the Sobel kernel, average kernel, and so on are symmetric kernels. So usually most of the kernels that we hand design are symmetric kernels. So as a result, the reflection is not required. So correlation and convolution are equivalent in that case. But then what about the convolutional neural networks? So in convolutional neural networks, mm, now you see when you run the convolutions in the convolutional neural network, you do backpropagation. And backpropagation, and you affect the kernels. You affect the kernels. The values of the kernels will be affected due to backpropagation. What that means is uh, the network decides what the values of those kernels are. And in the learning time and in the inferencing time, the same kernel will be used. So therefore, if it is the reflected version that the kernel has had to be imparted with, the network will do that. So therefore, in that case also, the concept of reflection is not required. But convolution essentially means that you have to reflect the signal, because if you look at the equation, either the signal or the system will have to be reflected. So here you can see H has been reflected. Okay, thank you.